Good morning, everyone. So we were looking at moving towards vectors and matrices. So these are all special cases of arrays. A vector is basically an array with only one dimension, and it goes up and down if it's a column vector, and it goes sideways if it is a row vector. Whereas a matrix has two dimensions because it has columns and rows typically. Though you could have a 1 by 1 matrix, in which case it looks just like a scalar, and it would then look like a vector, etc. Okay, so each of these things can be kind of stacked up into broader and broader levels of generality. And then when you get into real abstract math, you find out that matrices are vectors too, and you find that functions are vectors and everything else, and you go like, whoa! But we're not doing that level of abstraction at this point in Rob 101 anyway. So we were looking at taking how you write down equations in terms of variables and then represent them in terms of matrices, because that's our entry point into be able to program effectively and handle things with hundreds of variables. Okay, so we want to write it like a matrix A times a vector X of unknowns equals a vector of constants. And the first step is you order the equations and you form your vector of unknowns as a column vector. So our unknowns, and I don't have to point at the, whoops, I got the wrong thing, darn. Okay. I don't have to point at the screen that the online people cannot see anymore, so I solved one problem. And by the end of the course, I will have solved 42 problems, right? That's 42 lectures. No. Okay, so our unknowns are y and z, and I stack them up into a vector x. Then we move all the constants to the right-hand side. R's are already there, and we form the matrix B. And then we get A by, let's remember the A sub ij notation for a matrix. The I is the row number, and the j is the column number. So the I is the number of the equation, because the equations are in rows, okay? And the j is the column number. And so if we look at this equation, A11 is the coefficient multiplying the first variable in the first row. A12 is the coefficient multiplying the second variable in the first row. A21 is the coefficient multiplying the first variable in the second row, and A22 is the coefficient multiplying the second variable in the second row. And we have succeeded in writing our equation in the form AX equals B. Okay, does that seem clear enough, the process, or does it seem like I'm treating you like you've never even seen mathematics before? I don't want to be teaching down to you, okay? So you can provide feedback on whether the level that we're going through stuff and the detail is too much, etc. So let's just do it live.
Beta, or are they just A?
Okay, that didn't come through very clearly. Maybe it was just a fluke. So type it, the question maybe in the chat box, please. Cool. So let's just suppose we change the order of the variables and we don't put y on top. Okay, we can do anything we want. I could have reordered the equations and put the alpha 2's on top, etc. But let's write this in the form of a matrix A. And then this is x, so this is z, y equals b. Since we did not change the order of the equations, b doesn't change. Okay, but we have changed the order of the variables. So what is the 1, 1 coefficient of A? Alpha 1. So what is the first coefficient in our vector x? That's z. So what is the coefficient in the first equation multiplying the first variable? Beta 1, yes, okay. So there's our first variable. So if you change the order of the vector, you change where the coefficients go. Okay, so once we get warmed up like that, so then we look at, we're still looking at, say, the first row of our matrix. We're looking at the first row of our matrix. Then the coefficient multiplying the second variable in our vector is then the alpha 1, okay? So that's alpha 1. And then we move on to the second row, and we look at what's multiplying our first variable, which is z, and then we would have beta 2, and what's multiplying our second variable, y. That is the alpha 2. Okay, so if you change x, you change the matrix. It's the same equations, okay, because this still means beta 1 times z plus alpha 1 times y. That's what that means. Beta 1 times z plus alpha 1 times y. And what this means is beta 2 times z plus alpha 2 times y. Beta 2 times z plus alpha 2 times y. Okay, so that's how you get the orders. And so order matters when you do the matrices. And the two matrices are not the same, because this one means alpha 1 times y, that's correct, plus beta 1 times z, beta 1 times z. And this one, alpha 2 times y, we see that here and here, and beta 2 times z, that's here. So that's how you just keep building these things up. So let's do another example. And I want to turn that off soon. Okay, so I'm going to give this one a title. Missing coefficients. They're not missing per se, but this will draw it to your attention a little bit more. And let's see if I can write this legibly. 2x1 plus 3x2 plus 5x3 equals 1. x1 minus x2 equals 2. And x2 plus 4x3 equals 3. Okay? And do I have enough room? I think we can squeeze it in and not be too terribly illegible. Ooh, it's going to be tight, but we only have small numbers to write there, okay?
Professor?
Question?
Yeah, I have a question. How did you get 2 and 3 from x1 minus x2 and then x2 minus 4x plus 4x?
So these are just my, my equations that I just made up. And what we're going to do is take, so I don't know if everybody heard the question. So how did I get the 1, 2, and 3 when I did x1 minus x2 equals 2 and x2 plus 4x3? So I'm taking the equations on the left-hand side as just somebody gave me a set of linear equations that I need to analyze. So all those numbers are completely arbitrary, and we have not solved yet for the x1, x2, x3. Okay, but we're going to set things up in a matrix, and that's going to allow us to solve these types of equations when we have 30 equations and 30 unknowns. Okay, so this is just getting us used to writing things like this. So these would be like drill problems. And then when we get into Julia and the week 2 and 3 assignments, you'll start seeing like, whoa, he's having us solve a set of equations with 50 variables. Yes, okay. But we don't make you enter all 50 by 50 coefficients by hand in the matrix, okay? That is not how engineers do things. Is that an adequate answer?
Yes, and also just so you know, I've never used those delta and alphas before, so I don't know the like differences between them.
Oh, okay. So the questions were about the Greek letters, alpha 1 and beta 1 and gamma. Okay, so alpha, beta, gamma, delta is the A, B, C, D in the Greek alphabet. And when people are doing mathematics, the 26 letters in the Latin alphabet gets kind of limiting, and so we start using Greek letters. And we have not moved on to Sanskrit yet, and Chinese, but we should probably, okay? So that's all those are. They're just other ways to represent unknowns. And for us, they're the constants multiplying the y and the z. Okay? Cool, thank you for asking questions and intervening in, and that's helpful for everyone. Okay, so now I've got these made up equations on the left, and I just want to define my vector of unknowns. And then once I get that order, I can start filling in all of the coefficients. Okay, so these are given, and now I need to fill in what is the A matrix, what is the X vector, what is the B vector. Cool, so everybody cool if we do x1, x2, x3 for the vector of unknowns? We could do it x3, x2, x1, or x3, x1, x2. It's your choice, but I prefer to put them in the order of the indexes, the indices. So this will be x1, x2, x3. Okay, so now that we've defined the x, and we're keeping the same order of equations, we can just put the constants over here. They're already conveniently on the right-hand side of the equation. If this constant had been written as -1 equals 0, we would have to bring it from the left-hand side to the right-hand side. Because unless we wrote the equation as a times x, unless we wrote the equation, see, my reflex is to go to the board. Unless we wrote the equation as a times x plus b equals the 0 vector, 0, 0, 0, but we're writing it as ax equals b. Okay, so now let's fill in the matrix. What multiplies x1 in the first row of the matrix? So that's the 2. Whoops. That's 2. And what multiplies x2? We have 3. And what multiplies x3? That's the 5. Okay. So when we look at aij, we go to the ith row and we look at the jth variable. So a13, we look at the third variable. And this a12, we're looking at the second variable, and a11, we're looking at the first variable. Okay, so now we're going to the second row of the matrix. What's multiplying x1? 1. the class says. And what's multiplying x2? -1. Now we don't have an x3 in that equation. What's multiplying x3? Everybody cool with that really means 0 times x3? That's really important, okay? We can't just leave that entry undefined. It's 0. This equation, if we do plus 0x3, we change nothing, okay? But we, as humans, when we're writing, we don't write out the 0 terms because they look boring and they interfere with us seeing the other terms, okay? It's all it is. It's just, it could be a convention that you have to write down every single variable. Fortunately, it's not, okay? So this is a 0. Let me put that in red just to be extra clear. So that's a 0. Okay, so now let's go to the third row of equations, which is the third row of the matrix. And you want to look at what's multiplying x1 in the third row.
0.
And the answer is yes. You guys are getting the hang of it, and you're probably going like, he's beating a dead horse. Okay, but that's okay. You know, that dead horse doesn't mind. It's plus 0x1, okay? And now, what multiplies x2? We've got that down. That happens to be 5, right? Everybody shaking their heads, it's 5? No, it's a 1, okay? And what's multiplying x3? -8, no, that's 4. Okay, so that's how we take given sets of equations and we turn them into a set of matrices. And this will put us in great shape for working on large systems of equations. Okay, so now I'm going to give us a situation where we have to build the equations ourselves, and then we convert them into matrices, just to make sure we've got this down. Okay, so now we build both the equations and the matrix vector representation. Okay, so in these previous examples, I just said, hey, somebody gave us this equation, and then somebody gave us this one, and they didn't even want to give us numbers, but it allows us to treat all possible real numbers alpha 1, all possible real numbers beta 1, all possible real numbers gamma 1, etc. Okay? This one we'll go back to doing numbers, and okay, so let me label my axes, x and y, and I'm going to start out with 2 data points. Whoops, I have graph paper, so I can do that. That's the point 1, 2, and I'll call that point x1, comma y1. That seems pretty natural. And then my next point is 2, 3, 4, 5, 6, 7 here, and I go up 5. 1, 2, 3, 4, 5. That's 7. That's 5. And that's x2, y2. Okay, so I won't make you do too many graphs like this, but what I want to do is fit a line to the points. I'm setting us up for some really cool problems later on. So this is particularly simple because I have 2 points, and 2 points determine a line. Okay, so that's, but I want a model of these points. Okay, so I have my x1, y1, and my x2, y2. x1, y1 is 1, 2, and x2, y2 is 7, 5. Okay, now what are the unknowns in this problem? You gotta speak up. Yeah, the unknowns are m, which is the slope, and b, the y-intercept. Okay, it's not x, it's not y. I gave you the values of x and y, okay? Oh, can we write this down as a set of equations? So there's the graph, and everybody can kind of see that we're after this line, okay? What is its slope? What is the intercept? So we just want to set up the equations. I'm not interested in solving them because you guys can do that offline. But if I were to write this down, the first set, we know that y is 2, m is unknown, the x1 was 1 plus b. So this comes from x1, y1 equals 1, 2. And I'll write down my other point, x2, y2, and that was 7, 5. Okay. It's all there. Fit a line to the points. And my model is that the ith y value is a slope times the ith x value plus an offset. And that offset is the y-intercept or something like that, okay? Well, we just fill in the equation. So yi is equal to 5, and that is equal to m times the x value, which is 7, plus b, which is the unknown. Okay, so I'm going to expand your notational horizons a little bit, because this is 2 equations and 2 unknowns. We could do easier. We could do 1 equation and 1 unknown, or we could do no equations and no unknowns. That's your favorite problem, okay? But you don't get paid big bucks to go out and solve that problem. And usually the 1 equation and 1 unknown gets you a paltry salary and very little intellectual and emotional satisfaction when you solve that one too, okay? So we need to do more. We have 2 equations, 2 unknowns. That's the next level of complexity. Now I want to write this as ax equals b. Now, I don't really want to call the right-hand side b anymore because b is what you've always used to call the y-intercept. So we're going to use just different variable names. But it's still going to be a matrix times a vector of unknowns equals something on the right-hand side. Okay, so I'm going to call capital Y, Y1 and Y2. Does that make sense? Yeah, okay. And so for us, that's the vector 2, 5. Okay, that's going to form the right-hand side of our ax equals b type thing. Now I'm going to define the vector of unknowns. Okay, and I'm going to set us up for a later chapter, and I'm going to use the Greek letter again, alpha, which is A in the Greek alphabet. Now I have 2 unknowns, M and B. What order do you want to put them in? Alphabetical, the first one that shows up in the equation. Everybody can do it differently. I'm just pointing out, like when we do x1, x2, x3, everybody knew the order they had to go in. Here, there is no right order. It's your personal choice, okay? There's a choice. So this is what I chose. Slope, and then the offset. Okay? So here's our equations. I'm going to write them as a matrix times the unknowns equals a set of constants, just like we've always done before. Okay, so let me get these down. Well, I guess it's okay. Am I blocking the screen for the people in the class badly? Everybody's cool? I know I'm not blocking it for the online folks. Okay, so what do you think the right-hand side is now? Yeah, it's 2 and 5. They started on the left. We can just move them either side we want. It's an equal sign, okay? It doesn't matter. Left, right, we just move them around. Okay, now what's the coefficient multiplying the first variable in the first set of equations? Oh, don't do that to me, please. Thank you. Okay. Okay, what's the variable multiplying the first unknown? It's a 1. And what's the coefficient multiplying the second unknown? 4.
7.
Here's the first set of equations. This is the second unknown. What's the coefficient multiplying that one?
1.
Yeah, 1. Okay. Now we go to the second, get out of there, set of equations. Okay, and our first unknown is m. What's multiplying m? That's the 7. And then what's multiplying b again? The second unknown, that's also 1. Okay. So, you see, we had to make a choice of what the unknowns were. We needed to identify them. And then we build up the set of equations, and then we write them in matrix form. So, this one we're going to do much more quickly. Whoops. So I still have the 1, 2. I still have the 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And then I'm going to throw in another point. 1, that's just 2, 3. And then I want to go 4. 1, 2, 3. Whoops, 1, 2, 3. Well, that's 4, so then this must be 5. So that's 3. That's 4. That's the 5 we had before. That's 7. So I have x1, y1 equals 1, 2, x2, y2, I'll keep it as the 7, 5 I had before, and even I can't read that. x2, y2, and x3, y3, that's 3, 4. Okay, now, how many points does it take to determine a line? It takes 2 How many points do we have? 3. So let's just go ahead and write them, and then we'll just, as a model, just like we had before, yi equals mxi plus b. Okay. We're going to call that y, and it'll be actually easier for us. So here's our unknown, called that alpha before. And vector y is just the y1s, y2, y3 all stacked up. So if I fill in the y, it's the y values, so I get 2, 5, and 4. Okay, so that's y1, y2, y3. y1, y2, y3. Cool. Here's my vector of unknowns, and I kept the same order that we had before. Same, so as not to cause mass confusion in week 1 of Rob 101. Okay, so let's fill in the variables. Okay, so what's multiplying m when the first row? Well, that's the x value, and that was 1. And what's multiplying b? That's always a 1 in every single row of the equation. And for y equals 2, x2 was 7. This is always 1. And then for y equals 3, we have x3, that's 3, and this is always a 1. Now, we have 3 equations with 2 unknowns. What typically happens when you have more equations than you have unknowns? Oh, okay. Well, you're supposed to be a model of a line. Which line should I choose to be the solution of the equation? That one? This one? Should I choose this line? Or would you want to choose something that averaged out the distances, okay? So imagine this is you taking data in your physics class. If you wanted to get the mass of something or whatever just perfectly and have no uncertainty, you would just take, I have one unknown, I do one measurement, and I just hope it's good, okay? But now you're saying, well, I'm not so perfect in my experiments. There's experimental error, so I take 2 measurements for that unknown. And then here, we assume like this is a resistor and current and voltage or whatever. We take multiple measurements, and then we're going to try to estimate our unknowns from the data. So this equation has no exact solution because there's more constraints than we have degrees of freedom, the unknowns to change. We cannot find a line. This is not a line, okay? It goes through all the points, but it's not a line. And so one of the cool things we will work on a little bit later in Rob 101 is how do we formulate an answer to this problem that has the least amount of error. And that'll be called estimation, okay? So writing down equations that have no solution is a very natural thing for an engineer. And then you try to find a solution to it that is approximate. And so y minus this gives me something that is as close to 0 as I can get. So I'm trying to satisfy the equations, okay? Anyway, what I just wanted to illustrate is these equations I just wrote down because they had nice numbers. Equations really come from data. if we have two pieces of data and two unknowns, no problem. We can always get equations that are consistent, and usually they work out nicely. And then when we have more data, because we're trying to allow uncertainty, then we get equations that have more constraints, then we have unknown coefficients, and this will be a linear system of equations with no solutions. That's fine. Okay, so just kind of a heads up of where we're going. Questions? This is a good place to pause for questions. Physically motivating, was that cool? Uncool? Confusing? Writing down equations that don't have solutions, that seems bizarre to you, or you're good with that? You got to think about it, okay? It's a philosophical point of view. But in engineering, as in life, anything interesting does not have a perfect solution. It's just the way it is, okay? And when we're taking data with our robots, we never know exactly where an object is. We try to estimate its position to a certain degree of precision. That's what we try to do. And we use equations like this, and that's where we're going. Oh, I don't know what that means yet. I haven't read you guys enough. Okay, we'll do a new topic, the matrix determinant. I should have put my phone on airplane mode, and I did not do that. Bad me. Okay. Okay, so we're going to let A now be an n by n matrix. And just to be super clear, real numbers. Okay, so because it has the same number of rows and columns, we also say that A is square. So the first fact, oops, fact one. Matrix determinant denoted det of A. Okay, so we put parentheses around something to show it's a function. We're going to call it det, short for determinant, is also a real number. Okay, so that's a real number. Okay, so this is going to be a function that operates on matrices and returns real numbers. We're going to see that what it tells us is, when does a system of linear equations have a unique answer? You've got 50 variables, 50 unknowns. You calculate one number on the basis of the matrix that's multiplying the vector of unknowns, and you determine whether or not the system has a unique answer. So that's just totally amazing, okay? So that's fact two. So fact one is it's a well-defined function that takes matrices to real numbers. Okay. Fact two. A square system of linear equations A, let me just separate it out so there's not bunched up. AX equals B. So square means n equations, n unknowns. Wow, that's super general, okay? N can be 1, 2, 3, 4, 5. It cannot be infinity, but it can be Avogadro's number, 10 to the 26 or something like that. Okay? It can be huge. A square system of linear equations that we write in the form AX equals B has a unique solution for any choice of B if and only if determinant of A is not equal to 0. Okay, so you remember when we were writing down things in the form of 3x1 plus 4x2 equals this, so writing out the equations. When it was two equations and two unknowns, we could do the plots, and if the slopes were different, they would intersect, they'd have a solution, so that's how we could do it. If they were parallel, there was no solution, etc. As soon as I got to 3 variables, we did the plot, and it was like really hard, and so then we'd have to go through and grind every row to determine what was happening, okay? That is not a pleasant thing, okay? What this is telling us, there's this magic function that we'll talk more about just in a minute, that you take the matrix, you operate this function on its coefficients, and you know about uniqueness of solutions just by checking whether that the answer when you apply that function is 0 or it's not, if and only if, okay? So that does it. So, given something like that, we'd like to know how to compute it. Oh, I'm jumping ahead. I should tell you what happens when the determinant is equal to 0. Okay, then we'll get to there. When determinant of A equals 0, AX equals B may have either no solutions or an infinite number of solutions. Okay, so that determinant can be any real number. It can be -5, and we have unique solutions. It can be plus 247, we have unique solutions. If it's equal to 0.01, it's still not 0, and we have a unique solution. There's one single value when we're kind of stumped. We don't know whether either the equations have no solutions or they have an infinite number of solutions. Okay. Chapter 7 will deal with these cases, okay? So we're going to punt the can down the road. We will have methods in Rob 101 in order to handle how do we decide when AX equals B has either no solutions or it has a whole infinity of solutions, meaning a whole line of solutions, a whole plane of solutions, a 7-dimensional crazy set of solutions. We'll be able to deal with that, but not for right now. So for us, either we land in this case, the determinant is not 0 and we get uniqueness, or we just say it's either this or that. We don't know which one. Okay, so it's unsatisfying. I understand that, but we're going to peel off the difficulties one by one and address them. So suppose the matrix is 2 by 2. Then the determinant of A is A times D minus B times C. Okay? So this is really an important formula for us. Okay, so then in a standard course on linear algebra, we would then look at the determinant for 3 by 3 matrices, 4 by 4 matrices, 5 by 5 matrices, 6 by 6 matrices. And we would teach you how to struggle by hand and compute the determinant for all of those different matrices, okay? We're not a standard course on linear algebra. What we are going to do is I will hold you responsible for the determinant of A of a 2 by 2 matrix. For a 1 by 1 matrix, the determinant is actually just equal to the value in the matrix, okay? So you need to know that as well. But we're not going to hold you responsible for calculating by hand determinants of things when in fact it's a useless exercise, okay? There's plenty of good algorithms available in Julia. But what we will do is we will soon move on to systems of equations that have special structure. These will be triangular systems. And then we'll learn that we can have a 50 by 50 triangular system and calculate the determinant by inspection. Okay. And then we will understand that if we have a 50 by 50 matrix, that we can write it as the product of two matrices that are triangular. And then we will know that the determinant of that 50 by 50 matrix is the product of the determinant of the first triangular matrix, whose value we can do by inspection, and the determinant of the second matrix, which is triangular, and whose determinant we can calculate by inspection. Okay, so that's the path we are going to take in Rob 101. It's a more sophisticated approach to the determinant, but that's the one we are going to do. Okay, so this is the end of lecture for today.